Okay, so we are learning about dynamic programming. And by the way, you should have received the feedbacks for test number 2. So basically, all of the students who attend all of the lectures here did pretty well for the test. And it's what I expected, okay? As If you have any question about any of the comments or suggestions I made, feel free to contact me. I'm more than happy to answer any question you have. So today we will continue with dynamic programming. Yeah, so last time we have one example that is about how can we find the best way to multiply a chain of matrices. Right? So let me remind you a little bit about what we did last time, and then we will continue with one more hands-on exercise, and then we will move to the next problem in that we also want to design a dynamic programming algorithm. So first, given a sequence of matrices, right? Given a sequence of matrices, okay, like we have A, B, C, and D here, where A has 30 rows, one column, B has one column, 40, one rows and 40 columns, etc., right? So multiplying four matrices, we have many different ways. For example, we can multiply AB first, and then after that with C, and then after that with D, right? If we multiply the matrices that way, it takes about 20,700 multiplication of the elements of the matrices, right? But if we multiply BC first, and then D, and then multiply with A, it takes just only 1,400 steps, right? So that said, finding the best way is what we want to do. And we did it by analyzing the problem, try to design a recursive divide and conquer algorithm, analyze the complexity, right? So that said, we know that if we have a sequence of matrices, we have many different ways to partition the list into two smaller sequences, right? We can cut it here, cut it here, cut it here, right? And then we just find out where we cut, whether or not it has the smallest value, right? So that said, if we want to find the smallest number of multiplication for this sequence, then we can call that number is Mij, where Mij is the smallest multiplication we need for a sequence from the matrix I to matrix J, right? So for a generic number, of course, what we want to do eventually is what would be the best way to multiply from A1 to AN, right? But so we have A1 to AN, but we need to break the sequence into smaller sequences and then apply the algorithm recursively. So we need to have a way to multiply a sequence from AI to AJ, where I from 1 to N and J from I to N, right? Okay. Okay, so that said, we can choose recursive algorithm, okay, find out the best way of multiplying the left subsequent, the best way multiplying the right subsequence, and then combine the results, right? Okay. So it reminds us that we can use divide and concur, right? The only problem with the algorithm here is a divide and conquer. Very simple, right? Finding the best way or the minimal way to multiply a sequence of matrices from I to J. Okay, P is the sequence of matrices, and we want to find out what is the minimum value we have to perform when we multiply the sequence from matrix I to matrix J, right? So if I equal J is the base case, and then we simply partition, okay, at any point and find out where we have the smallest, right? So that's set for every k from I to J minus 1. We just invoke the function again from I to k and from k plus 1 to j and combine the two subsequences together, right? Meaning that we multiply the matrix that we have from the left sequence, left subsequent, and the matrix we have from the right subsequence together is where we have this number. But this one, we have just big O1, right? Yeah. Okay. Now, last time we analyzed the complexity, and it turns out that is Tn is 3 power to the n, right? So, and this one is similar to try all possible, cases, right? Like the brute force. So having the recursive algorithm is not better than try every possibility. And the reason for that, we already know, is that when we invoke the submatrices, some of the calculations will have to be repeated again and again. And that is a waste of time and memory space, right? Hence, last time we tried to design a better algorithm that will take big O and quit instead of 3 power to the n. Okay? What we can do is that instead of recalculate the values mik and mk plus 1j, we simply store the value we calculated before and just look up and use the intermediate results instead of recalculation. Okay, so that was what we had before when we tried to find out what is the best way to multiply these four matrices. Okay, so last time we went through the steps and then find out that, okay, so we go diagonal by diagonal, right? And finally, we reach this point, and that is the number of smallest multiplication we have to perform. And at the same time, here we have the cost matrix, and here we have the position matrix, right? On the position matrix, we keep track of where we did the partition in order to have the smallest value. So after we have this matrix, we know that the smallest number of multiplication is 84. And the way we multiply the matrices are, okay, from 1 to 4, we first partition at 1. So that's said, we partition at 1, multiply the last 3 together, right? So 2 to 3, 2 to 3, okay? So here we have, 2 to 4, 2, 3, 4, okay? 2 to 4, we break it at 3, okay? 1, 2, 3, meaning that we break it here. So that said, we will multiply this matrices first, and then multiply with the last, and then finally multiply with the first. Then we would have the smallest number of element multiplications, right? Okay, so that is what we did last time. And again, the idea is we have to multiply a sequence. We break the problem into smaller problems, but we keep storing or memorizing the intermediate results. What would be the smallest value when we multiply two matrices, three matrices, right? Two matrices from 1 to 2, right? And then from 2 to 3, from 3 to 4, and then the minimum cost from multiplying three matrices, 1 to 3, 2 to 4, right? And finally, the cost for multiplying the sequence from 1 to 4, 1, 2, 3, 4, okay? Okay, so that is what we did last time. And today, we will work through the hands-on exercise that I asked you last time, right? Do it as an exercise at home before you come to the class today. So you see that the sequence is a little bit different with what we had before. Okay, before we have 3, 2, 2, 4, 4, 3, 3, 5. And now we will practice with this 2, 2, 2, 3, 3, 4, 4, 5. Okay, so who did it at home? Okay, so all right, very good. So what did you have here at this cell? What value do you have? 76? Okay, very good. 76. All right, so looks like you have a correct answer. So let's try a little bit different, okay? Actually, I implemented the algorithm already. So let me run it through and then we will see what will happen if we change the value a little bit. So we have uh, uh, okay, so let's see, we will have the following thing. I will change this one a little bit to 4. Okay, so we will change this one to 4, and then we will practice. Okay, so we have 2, 4, 4, 3, 3, 4, and 4, 5. Okay, so I'll let you redo this new problem for about, say, 3 minutes. I think it's enough. And then we will come back. I will come back and go through the solution with you to see how can we put the parentheses in. Okay, so how can we put the parentheses in like this, right? To find out what would be the best way to multiply the matrices. Okay, so what do you have for this cell? The last one. '88. Sounds good. All right, very good. Okay, so let's go through the solution so we know, I mean, how we can help it, right? And by the way, it's very important to follow the algorithm. Uh, for example, in the test, when I ask you to list the number of courses that will preserve the constraints for the prereq, right? So some students try to, I mean, find out a solution in an intuitive way. That may work for some small example, but for this kind of example, it's not easy if you don't follow the algorithm. Okay, even if you follow the recursive algorithm, it will take a lot of time. So that's why it's very important to understand the dynamic programming algorithms and then follow the algorithm correctly. Okay. That's why we have the hands-on exercise here for you. So let's go through the step, right? So we have here the matrix we have is 1, 2, 3, 4. So here we have 1, 2, 3, 4, and again 1, 2, 3, 4. Right? So first, we will try to find out what is the minimum cost for multiplying the sequence of matrices from 1 to 1. 1 to 1, we have one matrix, so the cost will be 0, right? So the minimum cost will be 0 because we don't have to multiply anything if we have only one matrix, right? So on the position, this one is for the position, right? Meaning, where do we partition the sequence so we can have this minimum cost? We have one matrix, there's no partition, so we don't have to fill it here, right? So we just leave it blank, right? So now we have all costs for multiplying two matrices. So we have first from 1 to 2, right? When we multiply two matrices, we have 1 to 2, right? So what would be the cost? We just multiply them, right? So we have 24, right? 2 times 4 times 3. So we have 24. Let me redo it so it looks a little bit ugly. Okay, so we have here 24. Now, the next one will be this cell, right? The next one will be diagonally, right? So we have 2 to 3, 2 to 3, okay? 4 times 3 times 4, okay? Okay, so we have 4 times 3 is 12, 12 times 4 is 48, right? So we have 48. There's nothing we fill in here, right? Because we have two matrices, we don't have to partition, right? There's only one way to multiply. So we don't fill in anything like that. So similarly, 3 to 4. 3 to 4, we have what? 3 times 4 times 5 is 60, right? So 60. Okay. Now we find out what would be the minimum cost for multiplying three matrices. Yeah, so meaning that three matrices from 1 to 3. So we are talking about this sequence. Okay, what would be the best way to multiply these three matrices together? So there are two different ways to break this sequence, right, into two parts. The first way is here. Okay, so we have the left and the right. So the cost would be, say here, this sequence has a cost from 1 to 1 is 0, right? Plus 2 to 3, we already have it here, 2 to 3, 48. Plus the cost for multiply the results together. So we have 2 times 4 times 4, right? Okay, so 32, 2 times 4 is 8, right? Right. So 8 times 4 is 32. All right, so the next is we break it here. So we have the left has 1 to 2, we already have 24. Okay, the right has 0, and the cost for multiplying them together is 2 times 3 is 6. 6 times 4 is 24. So clearly the blue one is smaller, so we don't even have to add them, right? So we just look and find out that the second way is smaller. So we have it 48. So we put it here, 48. Right? And then we know that here we cut it at this position will give us the smallest one. So we write down here the position where we cut the sequence, right? So similarly, we need to find out the value for this cell, right? So we will do the same thing. Okay, so here we have the sequence from 2 to 4, and hence we have two different ways to partition it. The first way is here. Let me erase this one. Probably I need to find a faster way to erase the value. Okay, but all right, anyway. Here we have from 2 to 4, right? So we go diagonally, right? So breaking here, we have the left is from 2 to 2. We know that is 0. And the cost for the right subsequence from 3 to 4 is 60. Plus the cost for multiplying them together, 4 times 3 times 5, 60, right? The second way is breaking it here, right? So we have 2 to 3. 2 to 3 is 48. Plus 4 to 4 is 0. We already know. And then the cost for multiplying them together, we have 4 times 4 times 5, right? 80. All right. So looks like the first one is smaller, right? So we write here, okay, 120 is should be 1. Okay, 120. and then we write here, right? So we break it at 2, right? Okay. Now the last one. Okay, the last one we have from 1 to 4. Okay. Now let's see if I can find the better way to erase this one. Yeah, okay, it's faster. Okay, so now here we have 4 different ways, right? So we can break it here. Let me take this color. Yeah, break it at 1. Then the left 1 is 0. The right 2 4 120. And the cost for multiplying them together 2 times 4 times 5, right? 40, right? Okay. The second way is here. Oops, need to change the color. Okay, we have 1 to 2. 1 to 2 is 24. 3 to 4. 3 to 4 is 60. And the cost for multiplying them is 2 times 3 times 5. Okay, 30. Okay, and the last one is here at 3. So we have 1 to 3. Okay, 1 to 3 is 48. Plus 3 to 4, 60. Plus the cost for multiplying them 2 times 3 times 5. Okay, 30. Okay, so looks like we have this one is smaller, right? Because here we have 60, 30, 60, 30, and here we have 24, right? So, oops, something is wrong. Something is wrong. Let me check to see what we have. Okay, so this one we have 0 plus 2 to 4 is 120. Yeah, we have it. And then the cost for multiplying them, 8 times 5 is 40. This one, 1 to 2, 24. And then 3 to 4 is 60. Right? And then the cost of multiplying them, 2 times 3 is 6. 6 times 5, 30, right? Okay. Okay. Yeah. The last one, we have 1 to 3 is 48. And then, oops, it's the wrong one here. It should be 0. Okay. This one is 0. 1 to 3, 48. Yeah. 4 by 4 to 4. 4 to 4 is 0. And then the cost, 2 times 4 times 5, 40. Okay. So here we have 40. Okay. So this one we have is 88. Right. So we have here 88. All right. And then the The best way to partition is at 3. So we have it 3 here. Okay. So let's double check it to see we have it right. 1 to 3, 48, 4 to 4, 0. And then the cost for multiplying them, 2 times 4 is 8. 8 times 5 is 40. So it's 40, and then 48 is 88. Okay, so looks good now. And we want to find out the best way by following the position, right? So first, we partition at 3. So we have it here, right? And now from 1 to 3, 1 to 3. Okay, here we have again 1. Oops. 1, 2, 3, 4. Right. So 1 to 3, break it at 2. Right. So that's said. Here is the best way to multiply this sequence of matrices. First, we multiply 1 with 2, and then multiply with 3, and then multiply with 4. And that's all we have with the minimum number of multiplication is 88, right? So we can double check to see whether or not using this way, we do have 88, right? So from here you have, what is the cost? Let me remove this one so we will double check the result. Okay, so if we follow this, we have the cost is 2 times 4 times 3, right? So 24. Oops. Okay, so after we multiply these two matrices, the cost will be 2 times 4 times 3, 24. And now multiply with the next, we have 2 times 3 times 4, right? 2 times 3 is 6. 6 times 4, 24 again. And then multiply with the last, we have 2 times 4, 8. 8 times 5, okay, 40. And the result is actually 88, right? So here we have 48, and 40 is indeed 88. Okay, so that said, multiplying this way do give us exactly the number, and we know that is the smallest number of multiplication we have. Okay, all right, so very good. So it's what we have for matrix multiplication. Is it clear? Any question about the algorithm we have? All right, very good. So that is what we have for matrix multiplication, right? Actually, multiplication of sequence of matrices. So the next problem we try to solve is related to a real-world application for assembling cars or automobile. right? I in I introduced this one before, but today we will try to design the algorithm and solve it. Right? So we have here a problem in that we have to find out what would be the best way for entering a chassis of a car, whether or not entering assembly line number 1, stay there, or entering assembly line number 2, stay there, or entering assembly line 1, go back to line 2, go back to line 1, etc. Maybe it's a better way, right? So here we have um, 2 assembly lines, and each of the assembly line will have some stations, right? For example, the first station will be welding of the body, and then the next station will be put on the driving wheel, and then the last one may be just, put on the wheels, right? Etc. So each of the assembly line will have a certain number of stations. So in general, we may have n station, right? So here we have, for the assembly line 1, we have the station S11, S12 until S1n. And then we have the second assembly line that will have station 21 to 2n. Okay? And if a chassis is entering line 1, it may take sometimes, right? Because assembly lines are in different places. So it may take, say, E1 time. E1 here can be, let's say, 2 minutes, right? To enter station 1 of assembly line 1. Okay. Depending on the workload at each of the station, it may take a certain amount of time for finishing that vehicle at that station. Okay? That is what we have for A11 is the time needed for finishing the work at station 1, right, of line 1. Similarly, we have A12 is the time needed for finishing the work at this station, right? So every station will have a time needed. So they are not the same, okay? Depending on who are working at that station, and also how many, say, chassis they already have at that station. So there may be a queue here, then the A12 will be bigger than A11, for example, right? If a car is entering the assembly line 1 and continue, if it goes from station 1 to station 2, it costs no time because it's on the same assembly line. It's just next to the other. So it will not cost any extra time. But if we try to move the car to another assembly line, then it takes time. Okay, that is what we have T11. That is the extra cost for moving a car from one assembly line to the other, right? And then after the car went out of a station, the last station of assembly line 1, it may take sometimes for, say, delivery the vehicle to a storing place. So in general, we call it takes X1 time. Yeah. Same thing for station 2, S2M, right? Assembly line 2, it may take X2 times for delivering the car, right? Okay, so that is what we have. And the question is, what would be the best time or the shortest time needed for finishing a new chassis. Okay? If you have a new car entering the assembly line, what would be the best way? Or what would be the shortest time? In general, it's not that you give the car to an assembly line and continue to do that. Okay? Sometimes it's not a good idea, okay? Because sometimes an assembly line may have some bottleneck. Okay? For example, at this station, for some reasons, there's a bottleneck there. It takes a longer time to finish at this station. And in that situation, it would be better to send the chassis to another one and then go back to the first assembly line. Okay, so that is the idea. And now we have to design an algorithm. Okay, and again, we will try to design the algorithm using exhaustive search first, and then we design the algorithm using divide and conquer, right? In that mostly by using the recursive algorithm. And we will analyze the complexity to see how fast the algorithm will be, and finally came up with what we call dynamic programming that will work much faster. Okay. By the way, in general, we may have more than 2 assembly lines. Okay? It may be 3, 4, or 5, right? And then the work or the values at every station will change. Yeah? It will be the real-time situation. It means that right now the value here can be, say, 10 minutes, but next hour it may increase to 20 minutes or reduce to 5 minutes. Okay? So that said, at any moment, we have a new chassis and we want to decide whether or not we send this one will give us the shortest time to finish the car, right? It's a real world application and it will have a lot of, say, a lot of things to help the car producers to increase their performance. And it's very important, right? Let me close the door a little bit. Okay, now let's try to design. Yeah, so we have the problem like that, right? So for example, here we have the real life situation, right? For example, if we have a new chassis entering assembly line 1 will take 2 minutes, right? And entering assembly line will take 4 minutes. And the current workload at each of the stations are as follows. So here we have 7 minutes for station 1 of assembly line 1, right? Okay, and etc. We have the numbers here. And then moving from station 1 of assembly line 1 to the next assembly line will take 3 seconds, right? Moving from 2 to 1 will take 1 second. So that said, at any moment, we know the workload at each of the station, and we know the cost for moving a car from one assembly line to the other, right? So we want to find out the best way or the optimal way to send a new chassis from entering to exit. Okay. For this particular example, if we go station 1 assembly line 1, go to station 2 assembly 2, go back, and then go out will give us the shortest time, right? So now the question is, how can we find this shortest time? Okay, here is one example. Now, how can we design an algorithm that will help us or help the car producers to find out the best way to work on a new car? First, we think about the exhaustive search, okay? I'll give you 2 minutes to think about the problem and one solution for helping the car producers to find out the best way to finish a car. Yeah. And the idea will work at this point. So that said, just think about any solution that can help us to design an algorithm, any algorithm. Okay, so and the idea for helping us to design an algorithm, DISRA, DISRA method. DISRA method is for finding the shortest path, right? Uh, from one end to the other. Yeah, it may work, right? Okay. DISRA method, so here we have the directed graph, right? Okay, so that said, given and entering, here's a node, right? DISRA actually can find the shortest path from any node to any other node, right? So, but if we find out what would be the shortest path from here to here, there's no way, right? But we can say that what would be the shortest path from here to here, okay? That is good. Okay, that is good. Actually, this algorithm is kind of dynamic programming already. Okay, so yeah, very good option, right? Now, how about exhaustive search? Yeah. If we want to try every possibility to find what would be the shortest path from here to here. So one way we can do is that why not try to formulate the problem in a way so that we can try all possibilities, right? So the easiest way is as follow. Okay. So we have two assembly lines, right? And then we just want to use one array that has n elements. And we will try to fill out the values here. Let's say we start with, here we have from station 1 to station n, and then we move from station 1 to station 2, right, etc. So if we denote that, if we want to enter station 1 of line 1, then we simply write 1 here. If we want to use station 2 of line 1 again, then we can write 1 here, right? But if we want to change from station 1 of line 1 to station 2 of line 2, then we can write it 0 here. 0 means the station 2 of line 2. Instead of 0, we can write 2, that's fine, right? But here we just want to say that there are two options, right? Line 1, line 2, right? Line 2, line 1. So that said, we will try to see here, station 1, we want to use line 1. And then move to station 2, stay at station 2, stay at assembly line 2, right? Station 2 of line 2, station 3 of line 2, and then station 4 of line 1, and continue. Right? And then finally, we are at the end, right? So in order to find out all possibilities, then we just need to have an array that will tell us that, okay, at this station, I choose line 1. The next, I choose line 2, right? Okay, and then next, I choose line 2. And then the next, I choose line 1. So that said, we have one array of n elements, and it will tell us about if we want to go from line 1 to line 2, etc. Right? And what we want to do here is that we want to try all possibilities, meaning that for this one, we just pick between 0 and 1. Okay, so the first possibility is everything 1, right? Everything 1. And the last possibility is everything 0, right? Okay, so that said, anywhere in between, it can be 0, 1, 0, 1, 0, 1, 0, 1, etc. Right? So for each of this specification, okay, this one is a specification about what assembly line we choose. Okay, for each of the specification here, we can calculate the cost. What would be the cost for this option? So let me remove everything here, and then we want to find out what could be the cost. If we follow these values, okay? So entering costs 2 seconds, 2 minutes, right? And then here we have 7 minutes, right? Go to line 2, cost an extra of 2 minutes. And then here it takes 5 minutes, and stay on. Here it takes 6 minutes, and go back to line 1, it takes 2 minutes, right? So that said, with this one, it will take entering cost 2 minutes. Oops. 2 minutes to enter, right? Station 1 of line 1 takes 7. And then go to line 2 takes 2, right? 7 plus 2. Right? Plus 2 plus the cost for station 2 of line 2 is 5, right? And then 6 and then go back to station 4 of line 1. Okay. 4, right? And then 8, then 3. Okay. So we have 2, 7, 2, 5, 6. Let's check it. Okay. 4 is 4. Okay, we missed 1 4. And then, oops, I think we have a different one. Okay. So here we have 2, right? 7, 2, 5, 1. Okay. And then oops, we go this way. Okay. So let me use this color so we will not get lost. Okay, go back here, stay, and then get out. Right? So the cost for this way, and we know that we have it at 1, 0, 0, 1, 1, right? Okay, and exit. So this way costs us 2 plus 7 plus 2 plus 5 plus 6 plus 2, okay, plus 4 plus 8 and plus 3. So it's the total number of minutes that they have to spend when we have this specification, right? 1, 0, 0, 1, 1, right? And then we just have to go through all possibility. For example, the other possibility may be here. So it can be 0 here, right? Okay. If it's 0 here, then we have a different way. And that said, we have 1, right? 0, 0, 0, 1, and then exit, right? So for this specification, the cost will be different, right? Like 2, 7, 2, right? And then 5, and then 6, and then 4, and then 2, and then 8, and then 3. Okay, so that is one way, right? So that said, we will try to find out how can we check all possibility, okay, by using a matrix or an array more precisely, right? And then we have all possibility. Each of the cell we have 0, 1, 0, 1, right? Okay, so the idea works, right? So that's it. We allocate an array of n elements, and then for every element here, we just switch the value from 0 to 1, 0 to 1, and calculate the cost and find out what would be the smallest value, right? Now, for that idea, is obviously the brute force, right? So what would be the total number of cases we have to consider? Meaning the complexity of the algorithm. 2 power to the n. Very good. Yeah, because each of the values here has 2 values. Each of the cell here has 2 values, and we have n of them. So it will be 2 power to the n. Right? Okay? So we have 2 power to the n. And it's exponential, meaning that the algorithm, if we have an assembly line with, say, 20, 30 stations, it will take forever to finish. Okay? Now, the other way that we can use is that we want to divide the problem based upon some observation. Okay? So the observation is here. What would be the best way to go from the entering into the exit way? So we will break the problem into smaller problems. So the question will be, okay, in order to go from the entering to the end, we may have to go through the stations here, right? So we just want to know the best cost or the best way to go to the exit path is based upon what would be the best way to go to the last station here, okay, and then the last station there. The best way to go to the exit would be the smaller value of going to this plus the extra cost, right? And the best way to go to this plus the extra cost. Now, in terms of a station, what would be the best way to reach this point? The best way to reach this point has 2 possibilities, right? One is here. If we find out the best way to reach the previous one on the same assembly line, then it will be the cost for reaching this one, right? And then going to this. Or the best way to reach this point plus with the extra cost for moving from one assembly line to the other, right? So that's said. The bigger problem is that find out the smallest time for reaching this point is partitioned into find out the smallest value reach this point, right? Compare with the smallest cost for reaching this point plus the extra cost of 2 before going to the other assembly line. Okay. So the original problem is broken into finding the smaller solution, right, on the same assembly line, finding the same solution on the other assembly line plus the extra cost. Compare them. The smaller value will be the best value for reaching this station, right? So that is the idea we have. Right? Okay. Okay, so that's it. The fastest time to go through is for this point. We call the F star, right? And in order to calculate that, we need to find out what is the minimum cost for assembly line I at station J. Okay, so that's it. Okay, so here the cost for this place will be the mean of the cost for F1N is here, right? Plus the extra cost, and F2N is here, plus the extra cost. The smaller value of these two values will give us the smallest time for reaching the axis point. Okay? So that said, this formula can give us, say, a divine concurrent recursive algorithm, right? The recursive algorithm for finding Fij will be, at the beginning, the base case is that for the first station, right? F1, meaning the cost for reaching the first station of line 1 will be E1 plus S11, right? Or A11 here. F21 will be this value plus this value. It's the base case. And the recursive case is simply here. F1 of J will be the smaller value of 1 of J minus 1 and A1J, meaning the cost here will be the smaller cost, and the smaller value of the value at the previous station of the second line, add with the extra cost for moving from one assembly line to the other, right? So that said, we have F1J will be the smaller value of going through the same assembly line or going through the other assembly line plus the extra cost. Okay. So we can write an algorithm in that this function will be called recursively, right? F1J will be F1J minus 1 plus A1J, or the smaller value of F2J minus 1, right? Plus the extra cost and the A1J, right? Okay, this one should be A2J. All right, so we have the recursive algorithm. But the problem with the recursive algorithm is that some of the calculation will be repeated again and again, right? And based upon this, the complexity of this algorithm will be also exponential. Okay, we can find out the complexity here, and it can be illustrated as follows. Okay? In order to find out the best way to reach the fifth station, we will go with F14 and then F24, right? Same thing, F25 here will be calculated using F14 and F24. So each of these, what F14 and F24 will be calculated 2 times, right? And from here, if we have the recursive call, it will be 4 times. The next one will be 8 times. The next one will be 16 times. Okay. So that said, if we have n station, then the calculation of F1 will be 2 power to the n again. Okay. So that said, using this recursive algorithm, we'll have the same complexity like what we did for exhaustive search. Yeah, so meaning we have exponential. Okay, so we will go to the dynamic programming by figure it out how we can store the previous calculation. So next time we will go through this dynamic programming, right? Instead of calculating 16 times, we just calculate them 1 time. Okay, 1 time, 1 time, and how to use the previous calculation for calculating the value we need. Okay. All right. So that's it for today. And by the way, we will have the training for the International Programming Contest today. So maybe we will have about 5 minutes break, or it's up to you, 15 minutes break. Which way you want? We will meet at 5. Okay, very good. So I'll see you then. All right. I will stop recording, but we'll keep the Google Meet on. All right. See you then. Bye bye.